¿Podemos ya dar inicio?
Sí, buenos días, por supuesto.
Okay, I'm going to do the introduction. Hello, everyone. The Faculty of Electrical and Computer Engineering is very pleased to welcome you to the new edition of CHARLA FIEC Online. Today, Professor Boris Ramos is going to present the topic Power Measurement System in a Microwave Link using SDR for rain rate estimation. Professor Ramos is a professional specialized in telecommunication with an interdisciplinary approach involving different science and engineering areas. He has more than 20 years of teaching experience at undergraduate and graduate levels in telecommunications, computer science, and telecom regulation and planning. In addition, he has more than 15 years of research experience in the following topics: modeling of rain rate using microwave, implementation of the wireless digital system using software-defined radio, studying the effect of environmental conditions on the propagation of wireless signals, channel propagation modeling and development of RF localization algorithms, system dynamic modeling of the telecom industry for planning and regulation, and analysis and implementation of IoT and wireless sensor networks. Please welcome Professor Ramos. You can continue, you can start with your presentation.
María Antonieta, Doctora María Antonieta Álvarez. This presentation is in English, and at the end we can have a conversation in Spanish if we don't mind. Okay, the title of the presentation is Power Measurement System in Microwave Link using Software-Defined Radio for Rain Rate Estimation. This paper was a result of our previous research in different projects, and it is the basically it comprises the validation of the implementation in different settings. Okay, my co-authors are Marisela Freire and Álvaro Bustamante. This paper was presented in the 7th International Conference on Software-Defined Systems of the IEEE. Yeah, okay, that's it. We can.
Hello, everyone. My name is Boris Ramos. I am presenting our paper, Power Measurement System in a Microwave Link using SDR for rain rate estimation. My co-authors are Marisela Freire and Álvaro Bustamante. We're all from Escuela Superior Politécnica del Litoral, ESPOL, from Guayaquil, Ecuador. Our paper presents part of the results obtained in the project so-called Modelamiento de la Intensidad de Lluvia utilizando un sistema de radio en la banda no licenciada UNII, un experimento piloto en Guayaquil. The content of the presentation is as follows. The challenge that we wanted to solve with our SDR system. Then we have the system overview that describes the setting of our project, its main elements, and the simulation results. Later, we'll see the algorithm that describes the system configuration parameters, and the system validation. Finally, we'll have the conclusions. The challenge addressed by our project consisted on the implementation of a power measurement system at the receiver side of a 5 GHz radio link located between the tropical cities of Guayaquil and Durán in Ecuador, South America. Our system had to be sensitive enough to capture the small power variations caused by weather conditions, mainly rainfall. In this picture, we can observe a typical cumulonimbus cloud common in the rainy season of Guayaquil. The distance of the radio link is 18 kilometers, where 4 rain gauges have been placed at different locations, approximately below the line of sight path of the link, and covering different areas of the cities of Guayaquil and Durán. We can find, going from west to east, the ESPOL main campus. We can see it here. Then we have the hill of Mapasingue at this location. the Kennedy neighborhood, the city airport, which is in this area, the Guayas River, here I am pointing this river now, and El Recreo neighborhood in Durán City, which is here, where the transmitter is located. The equipment used in the transmitter and receiver of the wireless link can be seen in this figure. On the transmitter side, I am pointing now to the transmitter. We have the MikroTik metal 5SHPM router. It is worth mentioning that this equipment does not transmit the signal continuously, but through bursts of information, which optimizes the link performance. And the antenna height is at 25 meters from ground level in Durán City. On the receiver side, now in showing the receiver side of the system, the National Instrument USRP 2921 device is available for the reception of the information. Using the Arduino Uno development board and a LM35 sensor that measures the temperature inside the reception booth. The height of the receiver antenna is 45 meters. And its location, together with the reception booth containing the USRP, is within the SPL campus in Guayaquil City. The cooling system of the reception booth is by means of air conditioning, and as it is known, the USRP's oscillators are susceptible to temperature variations. So when designing and implementing the system, this issue must be considered. Directional antennas were used with vertical polarization, both for the transmission unit located in Durán and for the reception one located in SPL, with gains of 32.5 dBi and 29 dBi respectively. The radio mobile simulation software was used to predict the behavior of the radio link under normal conditions without the presence of rain and determine the coverage area. The tables observed at the top of the slide, these tables show the parameters defined for the transmitter and receiver used in the simulation. The frequency range for the simulation is between 5.51 gigahertz and 5.53 gigahertz. The table at the bottom of the slide, which I am showing now, shows the results of the simulation carried out in radio mobile. For the first Fresnel zone free of obstructions, it can be seen an estimated received power of minus 67.5 dBm and an approximate total propagation loss of 139 dBs for our 18 kilometers link. At the end, it was concluded that the parameter values described in the tables at the top of the slide meet the requirements of the link, considering, of course, the sensitivity of the receiver. The received signal acquired by the USRP is processed to generate the received power data by programming in LabVIEW. The preliminary training tests for the implementation of the algorithm corresponding to the calculation of the average received power were carried out using the equation shown at the top of the slide inside a laboratory, where N is the number of samples to be considered in the calculation. The results obtained from this test were satisfactory. The lab setting initially considered two USRPs, one acting as transmitter and the other as receiver. Finally, we proceeded to include an Arduino temperature sensor to the system. Later, we took our implementation to an outdoor environment, where our system proved to work properly in a real scenario. In this case, the MikroTik metal 5SHPN equipment was used as transmitter. Due to the observed low transmission power of the USRP, then it was confirmed the bursting transmissions of the MikroTik equipment. This situation implied a modification of the algorithm to assess the received power, as it was defined by the equation located at the top of the slide, which I am showing now. The figure at the bottom of the slide, which I am pointing now, shows the burst of data generated by the MikroTik transmitter. Therefore, it was necessary to modify the initial algorithm that implemented the equation shown at the top of the slide. We had to modify the original algorithm. This modification consisted on detecting the beginning and the end of the frame, this frame, which I am showing now, where there is a signal or packet. This was achieved by establishing a filtering threshold of plus minus 0.0025 in the complex amplitude of the received signal, managing to differentiate the noise and unwanted interference from the signal. This figure shows the flowchart of the implemented VI for the received power calculation. Once the Arduino is enabled and the USRP is initialized, as indicated by this block of the flowchart, the USRP starts to continually listen for a signal until its level crosses a predetermined triggering level. This procedure, or this function, is shown in this block of the flowchart. Then the data is captured in the next block and used to calculate the average received power using the procedure described in the previous slide. This function, this procedure is indicated in this block. Placing a timestamp and the temperature sensed by the Arduino for each iteration. The sensing temperature of the Arduino is indicated in this block, which I am showing now. Finally, the received power measured by the USRP with its corresponding temperature and time are saved in an Excel file for further analysis and assessment of the link attenuation. This function is shown in this block of the flowchart. A picture of part of the block diagram of the LabVIEW VI that implements the algorithm described in the previous slides is shown here. Here we have the system configuration parameters. At the top of the slide, we observe the parameters of the reception system, which indicate the sampling rate of 10 megahertz, the carrying frequency equal to 5,520 megahertz. The gain of the receiver is 30 dBs. The number of samples is 10,000. At the bottom of the slide, we have the parameters of the transmission system, which shows the transmitted power of 31 dBm. The passband bandwidth is 5 MHz. The protocol is N-string V2. The carrier frequency is 5,520 MHz, and the operation band is 5 GHz. Our first case for system validation consider the estimation of the rain rate using an equation derived from the ITU recommendation P.A38. Then the estimated rain rate in millimeters per hour is obtained using the equation shown here in the slide that is related to the actual average attenuation along the link, considering 4 rain gauges, where A total is a measured link attenuation. K and alpha depend on the frequency, antenna polarization, temperature, and delta X is a value that changes according to the time resolution used for processing the data, which is 1 second. In the figure shown at the right of the slide, the radio link recorded a rain event observed simultaneously in 3 rain gauge locations, specifically at Spall, Mapasinghe, and Kennedy sites. This event was able to generate radio link attenuation data that was transformed to estimated rain rate using the equation shown at the left of the slide. Later, it was compared with the average measured rain rate obtained from the rain gauges. The correlation for this case was 0.8475, which means that both events are strongly correlated. Therefore, the functioning of our SDR system was considered valid by the implementation of this procedure. The second validation step of our SDR system uses a recurrent neural network, RNN algorithm. The training algorithm used for RNN is the long short-term memory, LSTM, which is used to predict the attenuation of the link. The LSTM network is trained using reverse propagation over time. Then the data set is divided into a training set the 70% of the time and the test the 30% of the time. The data has been taken using the attenuation and temperature processed by our SDR system and humidity from public weather records. Once the model is established, the simulation is executed, obtaining the results shown in the figure at the right of the slide, which I am showing now, where you can see the light blue line that represents the actual attenuation. Now I'm showing this line. Taken by the SDR system. The orange line represents the attenuation data used to train the RNN procedure, which I am showing now. And the green line represents the attenuation prediction data per minute. I am showing this now. It can be seen that the green line and the reference light blue line are similar, indicating a good algorithm prediction in a preliminary manner. When performing the link attenuation training and prediction, it was obtained the root mean square error as defined by the equation indicated at the left of the slide, which I am showing here. Now, in this case, an error of 0.23 was observed for the training data set and an error of 0.12 for the prediction data set, as indicated in the figure shown here in the slide that I am pointing now. These results determine a good performance of the RNN procedure and imply that this model clearly reproduces the curve of the actual attenuation data measured by our SDR system, which successfully complete our second validation process. Finally, we have the conclusions. Our SDR power measurement system proved to be valid, capturing levels of attenuation with high resolution level. The high resolution attenuation measured by our SDR system allowed to accurately estimate rain rate using a 5 GHz frequency band, applying a ITU recommendation for this purpose. In addition, when predicting the attenuation values using a recurrent neural network algorithm, we obtain low root mean square error that determines a very good match. This successful validation procedure implies that our SDR system was sensitive enough to capture small power variations expected at the 5 GHz band due to weather conditions. And this is the end of the presentation. Thank you very much for your attention. Goodbye.
Thank you, Boris. Any question, you can write in the chat. It can be in Spanish, in English.
I cannot access the presentation. Okay, any questions?
I have a question, if I can perform it just by talking, if I can do that. Do I need to do it by the chat?
Who is this?
Oh, this is Tani.
Oh,
hello,
Tani.
Dr. Ramos. Nice to hear from you.
I cannot see it now. Okay, hi, Tani. How are you?
Very good. This is actually a really good presentation. Thank you so much for sharing this information with us. So my question is related to the second process, the one related to the machine learning approach, but using neural networks.
Okay.
I think it's in the slide 11, if I recall correctly.
Okay. Let's see. Here.
Oh, 12, yeah. Yeah, so it does look like the estimation through neural networks is actually very accurate and very close to the actual attenuation of the link. I was just wondering if you tested this approach in some other data, because this seems like this is around 44,000 minutes, correct? So I was just wondering whether this was tested in another set of data, if it was also validated through kind of like at different times, and what were probably the challenges on performing the training and the testing process within this neural network?
It's a good question. Actually, this is our best result that we had, but we, one of my co-authors could clarify this for me, Marisela. You can ask Marisela later, but I have I think we didn't have enough data also. Our time frame for analysis was somehow limited, but the results were also good. We picked, I guess, I remember, as far as I remember, the best results of the analysis. So we did. I'm sure we did different experiments, but yes, we had more information to process. Yes, that's the question. We did process, but we ended up with this result, which is the best one. I hope maybe we can talk about it later.
Sure. No, yeah, that was actually very useful information too, because yeah, just my question was more kind of like leaded towards just thinking that usually the neural networks do require a lot of information for the training process. And this one seems that it just had perfectly enough amount of training observations to perform really good during the testing process. So that's why I was just a little curious about it.
Yes, 4,000 minutes is kind of a good amount of data. So several hours of information. Mm-hmm.
Thank you.
Days, actually.
Thank you.
You're welcome. Any other question?
Hi. Yes, I have a question. This is Jorge Brito.
Jorge,
hi. Good morning. Yes. Hola. Yes. I guess I should, make my question in English, or Spanish is good. I don't know how's the protocol. Okay, because it's okay. Yeah. No, it's okay. It's okay. Yes, I guess the whole event is in English. So yeah, it's a simple question. The thing is that I kind of arrived a little bit late. So I just wanted to know when it was, when this data of the rain gauges was collected. It was in a, like a period that it was kind of, it was a closed period. It was this year, last year. It's historical data. Just wanted to know that.
This is mainly from 2017 in the rainy season, in April and March. And we got some few data in 2016. We started to prove our concepts in 2016.
Okay, so it's the 4 rain gauges, the one from, because of course you know that I've worked a little bit in this.
Yeah, actually,
as well.
I had to say something. Tani, who just spoke, she was part of the project, and also
okay.
I want to thank her publicly for her contribution in this work.
So it was using the 4 rain gauges, that the one from Kennedy, the one from Spol, the one from Duran, and the one from, I don't know which is the one that I'm forgetting about, but the 4 original, right?
Yeah, we had one in Espol, Mapasinghe, Kennedy, and Duran.
Okay. Okay, so it's the same position. It's not that you changed the positions. It's the same positions that were used for the 2015 and 2016 study, right?
Correct.
Okay. Okay. It's very. I think it's very good results, because you used a different equipment, you can say. Now it's a virtual one. SDR.
One interesting thing is the sensitivity of the system. Working at 5 gigahertz is especially when measuring, when modeling rain rate, you know about it.
Of course, yes.
You need
it's kind of tricky.
A very good resolution, because the fluctuation of the attenuation are very low, because you cannot use the RSSI of any equipment, because
it will be it will.
They have 1 dB resolution, so we cannot measure the amount of rain rate with that kind of resolution, because as I told you, this resolution is 1 dB. So we had a fantastic resolution with the National Instrument equipment. Remember that we have a 16-bit resolution of the information with this equipment. So it was perfect for the project. So for the purpose of capturing the data was very good.
Okay, it's and the time frame, it was a couple of months that you collect rain, like you said in 2017, the time frame of the data.
Yeah. In 2016, we gathered a couple of days, but in 2017 we were able to gather several days, maybe month, I guess. We gather information.
Okay. Thank you.
You're welcome. Any other question? So no more questions. So I don't know, maybe we can keep talking later with anyone because this project is still alive. We have a second part of this project. We are trying to continue. So we're looking for, by the way, we're looking for a network of radio wave links, microwave links. So we're in this stage. So we're trying to continue with the project as the second part. I mean, as a second part, as a second stage. So we have one requirement what we need to complete, which is finding the network of microwave links. It hasn't been easy, but we are moving forward. We will get these links sometime soon. Okay. See, if anyone is interested in this project, let me know and we can talk.
Thank you, Boris. Excellent presentation. Before we leave, please, we're going to take a photo.
I didn't turn on the video. Sorry for this. Let me stop sharing.
If everyone it's possible to open the video to.
Sorry for the video. I didn't open the video.
Nice. Who's the control? Maybe we can put all together in the screen.
So, hola Luis.
Hey, hello Luis.
Hey Boris, hey Maria Antonieta, nice seeing you. Very nice presentation, congratulations.
Gracias, thank you.
Okay, so we invite you to on your webcams in order to take a photo for our social networks. So in a count of 3, we have to take this screenshot. So don't be shy, turn on your camera, please. Thank you. Okay, we see that more people have to enjoy that. So in the count of 3, don't be shy, just smile. 1, 2, and 3. Okay, let me take another photo. On the count of 3, 1, 2, and 3. Thank you. Thank you, Dr. Boris.
Gracias. Muchas gracias. Hasta pronto. Y gusten verla, Tani, también.
Gracias, Boris.
Un gusto verlo también, doctor.
Estamos ahí. La próxima vez la pongo ahí. También usted tiene que estar en un paper porque nos ayudó. Y la verdad es que se fue ya a hacer su doctorado y quizás... ¿Cómo le va? ¿Ya termina?
Me falta un semestre. Ahorita estoy terminando justamente el penúltimo semestre y ya el próximo semestre ya, probablemente en mayo creo que ya estoy sustentando.
Felicitaciones.
Gracias. Sí, ya falta poquito. Yo digo falta poquito.
Adelante.
Gracias.
Excelente.
Muy linda la presentación, doctor. Me interesaba mucho saber también qué se había hecho en el proyecto y justamente me interesaba ver si se había aplicado algo de aprendizaje de máquina. Y sí, al parecer funcionó bastante bien, ¿verdad?
Sí, era importante hacer esa prueba. Sí, funcionó bastante bien.
Muy interesante, de verdad, muy interesante.
Excelente, gracias, Dani.
Bueno,
espero que se encuentre bien. Bueno,
claro, sí.
mucho gusto verlos a todos y estamos en contacto.
Hasta luego.
Sí, gracias, gracias, Boris. Hasta luego.
Hasta luego.
Hasta luego.
Muchas gracias. Hasta luego.